Bridge design and construction, spanning the gaps. Bridges are essential structures that overcome physical obstacles, enabling transportation and connection across rivers, valleys, or roadways. Their design and construction is a complex field of civil engineering, relying heavily on principles of physics and material science. Reinforced concrete, RC, bridges represent a significant portion of modern infrastructure globally due to their durability, cost-effectiveness, and versatility. The process typically begins with a thorough site investigation, analyzing soil conditions, water flow, and potential environmental impacts. This informs the choice of bridge type and foundation design, crucial for supporting the immense loads they bear. Following this, detailed structural calculations are performed using software like finite element analysis, FEA, to determine optimal dimensions and reinforcement requirements. RC bridges aren't simply poured concrete. The reinforced aspect is vital. Concrete excels in compressive strength, resisting being crushed, but is weak under tensile stress, stretching forces. Steel reinforcing bars, or rebar, are embedded within the concrete to counteract this weakness. These rebar cages provide tensile strength, allowing the bridge to withstand bending and shear forces caused by traffic and environmental loads. Construction often involves creating temporary support structures called falsework. This supports the weight of the concrete while it cures, hardens. Different pouring methods exist, including cast-in-place, where concrete is poured directly into formwork on site, or precast construction, where sections are fabricated off-site and then assembled. Several bridge types utilize RC effectively, each suited to different spans and conditions. Beam bridges are the simplest, consisting of horizontal beams supported by piers at either end. They're effective for shorter distances. Slab bridges, a variation, use a flat concrete deck acting as the main load-bearing element. For longer spans, cantilever bridges employ two opposing cantilever arms extending from piers, often meeting in the middle. These distribute weight outwards and require less false work during construction. More complex designs like arch bridges transfer loads to abutments through compression, requiring strong foundations but offering aesthetic appeal and efficiency. Finally, suspension bridges, while typically steel-based, often incorporate RC for deck construction and anchorages. The functionality of each bridge type hinges on how it manages forces. Beam and slab bridges primarily rely on the strength of their materials to resist bending. Arch bridges cleverly convert vertical loads into compressive forces along the arch's curve. Cantilever bridges utilize a balance of tension and compression within the arms, requiring careful engineering to prevent tipping or collapse. Suspension bridges distribute weight through cables anchored to massive towers and abutments, minimizing stress on the bridge deck itself. Understanding these load paths, how forces travel through the structure, is paramount in ensuring stability and longevity. Modern advancements are continually improving RC bridge technology. The use of high-performance concrete, HPC, increases strength and durability, reducing maintenance needs. Techniques like pre-stressing, where steel tendons are tensioned before concrete pouring, further enhance load-bearing capacity. Furthermore, incorporating sensors for structural health monitoring allows engineers to detect potential issues early on, preventing catastrophic failures. Bridge design is a dynamic field, constantly evolving to meet the demands of increasing traffic volumes and environmental challenges while prioritizing safety and sustainability. Vocabulary list. Questions. Choose T for true or F for false. 1. Reinforced concrete bridges are generally more expensive to build than steel bridges, but offer superior longevity. 2. A site investigation is primarily concerned with the aesthetic appearance of the bridge location and its impact on local views. 3. Rebar within an RC bridge provides compressive strength, while concrete handles tensile stress. 4. Falsework refers to the permanent structural supports that remain in place after a bridge is completed. 5. Cantilever bridges are typically used for very short spans due to their limited load-bearing capacity. 6. Arch bridges rely on tensile forces within the arch structure to transfer loads to the abutments. 7. Load paths describe how forces travel through a bridge's structural components. 8. Finite element analysis, FEA, is a software tool used to simulate and analyze stress distribution within a bridge design. 9. Pre-stressing involves reducing the tension in steel tendons after the concrete has fully cured. 10. Structural health monitoring utilizes sensors to detect potential damage or weaknesses in a bridge over time.